This video is going to show how to do the book case in R. Okay, so I've already brought the data in. You can get this data from Canvas, and I've called it book. So you'll see what we have here is number of items, the amount spent in euros. We have a recency frequency segment identifier, and then whether the customer was in a treatment group or control group. So the treatment group got a new customized promotion. The control group got a one-size-fits-all promotion. All right, describe the experiment. Is it paired or unpaired? Well, this is an unpaired experiment because we have two independent groups. The people who got the customized letter are independent or different from those who got the one-size-fits-all. All right, we have to define a new variable response that equals 1 when the customer is responded. So the way I'm going to do this is say book $response, or if you want to, if you don't like to type a lot, let's just say buy. Buy indicates whether the customer bought something. And one way to do this is I'm going to use as numeric book $tote euro greater than 0. So that's a Boolean expression. Let's do a summary on book now. And what you're going to see is that about 5% of all people bought. So the mean is 0.054. Remember, the mean of a 0-1 variable is the fraction of ones. And that's going to correspond to the fraction of cases where tote euro is greater than 0. So you see that the third quartile, all the way up through the quartile, the value of tote euro is 0, but there's a fairly large maximum value. So over 95% of the values of tote euro equals 0. All right, moving on. Define a new variable. Okay, we just did that. We have to run a crosstab of response in the columns and tx in the rows. So there's a couple ways to make crosstabs. Let's use x tabs. I give it a formula. So tilde tx plus buy. And the data set is book. Now this gives us counts. So these give the number of counts in each of those four possible combinations. If I do prop.table tab, and I want row percent, so I want a condition on tx, this is going to give me response rates. So in other words, 5.7% of those in the treatment group responded versus 5.28% in the control group responded. All right, so now we have some basic descriptives. Part D says construct 95% confidence intervals in the difference, and part C was test at the 5% level. Well, in R, we can knock off both part C and D with one command. So that's the t-test command. So my t-test is going to be, we want to have buy as a function of the treatment, and we need to give the data set name, which is book. Now, a minor point is we assume that the percents are equal, which implies the variances are also equal. So if I should add the argument var.equal equals true. And this tells R that I want to assume equal variances and form one grand estimate of the standard deviation. Okay, so what we see here are the response rates. And those response rates are the same ones that we saw up here in the crosstab. The p-value is very small, less than 5%, less than 1%, indicating we're going to reject the null hypothesis and conclude that the response rate in this treatment group is higher. That 5.7% is higher than the 5.28%. So it looks like the treatment worked. How do I get the confidence interval? Well, here's the confidence interval for the difference. The thing to note about this is that 0 is not in it, so we're going to reject the value of 0. 0 means that the difference between the treatment and control is 0. So we're going to rule that out. Let's read on. In the future, the company would like to be able to estimate the margin of error of the response rate for a certain offer within 5%, 0.5% at the 95% level. How large of a sample should be used? Well, remember the formula, z squared sigma squared over e squared. So 95% confidence means 1.96 squared. Now I need sigma squared. A conservative estimate of what a typical response rate, the most we'd ever get would be something like 5.7 or maybe 6%. I'll use 6% as to be a little bit conservative. So times 1 minus 6%, which is 0.94. And then I have to divide by e squared, so 0.005 squared. That's coming from this, so 0.005. I need a sample of about 8,500, 9,000, somewhere in that region is correct. Now, the most common mistake that students make on this is that they'll just assume the worst case, which would be 0.5 times 0.5. Now, if you do that, it says you need 38,000. That's much, much larger than what you really need, which is in the neighborhood of 8,000 to 9,000. All right. So in addition to studying response rates, the company also wants to determine whether it increases the amount of the order. So we're to study the order amounts for only responders. So in SPSS, you have to do a select cases. In R, there is a subset command. So this part asks us for box plot. So let's do a box plot. We're going to do tot euro as a function of whether the person's in the treatment or control group. The data set is book, and I can add an argument subset. I can add the subset command to any function that takes one of these formulas with a tilde. So subset is equal to, I like to stick it in parentheses, tot euro greater than 0, or I could just say by, because we've already defined this thing. All right, if I do this, let's go get the window up. There's something wrong with this. Let's go back to what I said earlier, tot euro greater than 0. What we see is that the distributions are highly right skewed, which doesn't surprise me since tot euro is an amount. Most people place fairly small orders, and then some place very large orders, but those are outliers. Part G says compute the log and then recompute the box plots. Well, in R, this is really easy. We don't even need to compute a new variable. I'm just going to take the log of tot euro. Now, in the instructions, it was to add 1 to avoid taking the logarithm of 0. We've already removed the 0, so that plus 1 is not completely essential. What we see is now the distributions for both the treatment and control groups are much more normal. We could potentially rely on the central limit theorem and work with unlogged values, but remember the CLT converges quite slowly when you have outliers like this, so I'd much rather work with the log distributions. All right, now we're to test the hypothesis. So is there a significant difference between these? Well, in R, it's quite easy. We're going to just change box plot to t-test. And this will pretty much work. I really should also say var dot, actually I don't want the var dot equal, just change it to t-test and we're done. All right, now we have the means of the logs. The p-value is not at all significant. That's way bigger than 5%. Therefore, I can't reject the null hypothesis that the basket sizes are the same, so the mean basket sizes are the same between the two groups. So I cannot go with the alternative that the true difference in means is not equal to 0. All right, so I don't have any evidence to say that the basket sizes increase. So my conclusions at this point are the treatment, so customization, increases response rates, but it does not increase the basket size. I don't have any evidence to say that. Well, let's go read on. There's also this RF segment variable. We have 4 segments in the data. We can run a table on this just to convince ourselves of that. So if you say book.rfseg, you'll see that there are 4 segments. And the question is, does the treatment affect response differently in these 4 segments? So I give some instructions for a graph in SPSS. The easiest graph to make in R that does basically what the SPSS graph did was the interaction plot. So we're going to make an interaction plot. And on the x-axis, I'm going to say book$RFseg. The trace factor we're going to say is book$TX. And then book$by is my dependent variable. So the solid line is for the treatment group. The dashed line is for the control group. And it looks like there's not much of an effect for the first 2 segments. These are your better customers. But the weaker customers show a bit more of an effect. Sometimes it helps to look at a different interaction plot. So if I switch the variables around, and I'm going to give myself some colors, 1 through 4. I mistyped something here. This needs to be TX, not RFTX. The change between here and here indicates the effect. So this line slopes up a little bit. The green line slopes up a little bit. The red and the black line are flat, telling roughly the same story as we had before. Well, that's a visual inspection. The question is, are these differences significant? So I'm going to go rerun that first t-test. Let's go bring up that first t-test again. So here's that t-test. And I'm going to add a subset command. So subset equals rfseg equals 1. So equals 1 is a comparison, a logical equals. This is just going to be on that first segment. And the answer is the p-value is greater than 0, so I don't have any evidence to say that this customization affects the first segment's response rate at all. Now we can repeat this for the second segment, and note the p-value is greater than 5%. Doesn't look like customization affects the second segment either. What about the third segment? Well, the third segment has a significant p-value. This is one of the weaker segments. It's the segment that's been lapsed for a year. So it looks like customization is effective in increasing the response rate of those who've been lapsed for 1 year. Let's check out the last segment, which is those who've been lapsed for more than a year, more than 2 years, pardon me. And the p-value is very highly significant, indicating the treatment, this customization, increases response rates among those who've been lapsed more than 2 years. Reading on, we're to now do this for basket size as well. So we could go look at the box plots. Let's go bring back that box plot command. Here it is. I can break this out by both treatment and rfseg by just adding that star operator to the formula. So now we have this is segment 1, and the box plots aren't very different. Here's segment 2, treatment and control, not much of a difference. What I see from the box plots is that there's not much going on. The medians are all about the same, so it looks like the treatment doesn't affect basket size for any of the segments. However, I haven't done significance tests yet, so let's go run those. So to run significance tests, let's go bring back my t-test statement, and we're going to add something to the subset command. So tote euro greater than 0 and rfseg equals 1. So here's that best customer group, the recent group, and the p-value is not significant, confirming what my box plots told me. Let's do it for segment 2. Again, p-value is not significant, so treatment has no effect on order size for segment 2. Segment 3, again, no effect. What about segment 4? Well, actually for segment 4, we have a borderline significant result. So it looks like the basket size is slightly greater in that group for the treatment group, the customized group, than the one-size-fits-all group, but it is borderline significant.